Okay, so our next example, as I promised on the last video, that I want to show you how can we sketch the equation which is non-linear, and the total variable that we have, there is 3. We have x and y and z. If as we discussed last time, if for the linear equation and there is a total variable, there is 3, so we should have tetrahedron. Now this is not supposed tetrahedron. We have another surface. Okay, so how the step. So what is the step that we have to provide? So what can you remember about the equation when the total variables there is 3? For example, we have discussed the paraboloid or the ball, the cone. So we need to provide 3 traces, right? So similarly for this particular equation. Okay. So as you can see here, so the x is just x squared and y squared and z squared. So meaning that there is no the x, the y, or the z, there is no the surface is not shifted somewhere along x, along y, or along z. Remember last time for the sphere, if you have x squared plus y squared plus z squared equal to 1, so we have a sphere with radius 1. But if we have x minus 1 square plus y squared plus z squared equal to 1, so for this particular sphere, it is shifted along x. 1 unit to along x, right? So now look at here. So meaning that if there is no I mean the x minus a squared, so meaning that it is not shifted somewhere. It's just, so we can say that we can have the x equal to 0. I mean the traces, we can set x equal to 0. Okay, so we start with the traces, 3 traces. So at x equal to 0, for this one, we have then y squared over 4 minus z squared equal to 1. Okay, I think for this particular example, I want to show on the new. Okay, so in this case we have x squared over 9 plus y squared over 4 minus z squared equal to 1. Okay, so the trace, so at x equal to 0, so then we have y squared over 4 minus z squared equal to 1. Okay, so remember last time I have on the part 1, the slide in the part 1, I give you the list of the basic function for single variable function. So now what kind of function that we have here? So this is hyperbolic, right? Hyperbolic. Okay, so what is the general form of hyperbolic function? So you must have something like y squared over a minus z squared over b equal to 1. So now we already have equal to 1. But now, do we have the denominator for z? Of course, we can always divide it by 1. So of course, we can find the denominator here, z squared over 1. So we can say that so it's supposed to be a squared b squared. Okay, so what is the curve of this particular hyperbolic function? So what is the curve? So the curve should be if I want to have z here and y here. So remember I told you before, how can we draw a graph? Whether the graph should be in this shape, or maybe we have this particular shape. So as I mentioned before, you have to look at the negative sign here. So now the negative sign belongs to z, so meaning that the graph never touch the z. So the graph should be never touch the z, so we have this particular shape. Okay, so what is the y-intercept here? So you have to look the value of a. So the value of a belongs to y, we have 2. So we have 2 here and minus 2. Okay. And then we go to the second trace, y equal to 0. Y equal to 0. Then we have x squared over 9 minus z squared equal to 1. Again, we have, just like on the zy plane, we have another hyperbolic shape. Okay. So now let's say we want to have zx. Okay, on the zx plane, we have another hyperbolic shape. And again, the negative sign belongs to z. So meaning that at this plane, the graph never touched the z. So again, here we have this shape. Now what is the x-intercept? So the x-intercept, then we have to choose this value. Square root of 9, so you got 3. So we have 3 and minus 3. Okay. And then we go to the next one. So the next one, we have z equal to 0. Z equal to 0, then we have x squared over 9 plus y squared over 4 equal to 1. So now they are all positive. So meaning that it could be either a circle or ellipse. Okay. But if it is a circle, so the denominator here should be the same. So that you can have something like circle equation when you bring this to the other side. But here you have different denominator, meaning that it should be an ellipse. Okay. So now you can see that how can you know the y-intercept and how can you know the x-intercept? So just look at the square root of the denominator. So this one at y-intercept it should be 2. On the x-intercept it should be 3. Okay, so we sketch the ellipse. So now we have y-x plane. So at y it is 2. At x it is 3. Okay, so we have x longer than y. So this one and this one. Then we draw the ellipse. So something like this, and this. Okay, that is ellipse. So now in this case, again about the level curve. In this case, it looks like we don't need the level curves. Okay, because we know that right on the floor, we can see when you are sitting or standing along the z, and when you're looking down, you can see an ellipse. So when you increase your height, so when you, okay, just now you say, okay, when right on the floor, it is an ellipse. So when you increase the z, which is maybe 1, so do we have another ellipse that you can investigate? Okay. Okay, so maybe you might wonder when when or how can we know that we have to sketch the level curve? So first, the question is the thing that you have to look at the instruction. If the question is purposely asking you to sketch the level curve for specific value of z, so you have to follow. Okay, but if the question is just say that sketch the surface of this particular function, for example, so you just sketch. But if you think that you don't need, I mean, if you think that it is okay, just like we sketched the bowl previously, right? So but for the bowl, we need to know further, because when you set z equal to 0, you got nothing. You just a dot. Then you have no idea. So you have to investigate further. But in this case, you don't need to investigate further, because you know that it is an ellipse. Okay. So whether you need to provide the level curve or not, so it depends on the situation. But the important thing is, if you have to read carefully the question, if they said provide or sketch the level curve for z, for specific z, then you have to follow. Okay. So now for this particular example, we don't need to sketch the level curve. It is because the question, okay, I didn't mention the instruction, right? I just want to show you how to sketch this particular graph. Okay, so that's why I didn't put the level curve at the moment. But after this, I have to explain back what is the complete surface of this. Okay, but at the moment, I just leave the level curve for a while. Okay, so now we have all these three graphs that at the end we have to combine them all together, isn't it? So that is what is the step that we have to provide, right? We have to find out the traces, and after that you have to combine all the three traces. In this case, we don't have the projection. Okay, projection only applicable for a single trace, but for three traces you just combine them. We don't have two traces. Okay, in our step there is no two traces. Okay, so now what happens if we combine them all together? So when we combine them, so let's say I fix to the standard orientation. Okay, we look at the first trace. So the first trace, when we set x equal to 0, so at equal to 0 meaning that you are standing over here. So what can you see? So what can you see? So you can see this, not that one. Okay, but this one, right? This one on ZY plane. Okay, so that purple, the purple hyperbolic, hyperbolic. Okay, the purple hyperbolic. Okay, so now where is purple? Purple, this one. So here and over there. Okay, for y negative. So just now we have, what is the y-intercept value? 2. So here 2 and this is minus 2. Okay, now we move to the second trace on the x plane, which means that you are standing over here. And you look at over there. Okay, so you can see another hyperbolic, the red one. Okay, so that is for x positive hyperbolic, and this for x negative hyperbolic. Again, so it looks compressed because we are looking from this side. Okay, actually that one is this one, hyperbolic. So on x you have 3, the x intercept is 3, and for x negative you have minus 3. Okay, and what can you see right on the floor? So now you are standing over here and you're looking downward. So you can see an ellipse. Right on the floor, you can see an ellipse. So now you can see the x-intercept. So you can see the x-intercept, so 3, and y-intercept, you can see 2. Okay, so now you have to combine all the intersection. So this one, that one, and that one. Okay, so here, now you have done combining all the traces. So as I mentioned before, sometimes it's quite hard for us to show exactly the ellipse that we want. But you can see from your trace. Okay, so as what I have been doing, I mean, when I mark your exam paper, okay, you are not around to explain back to me, right? So I 100% refer to whatever you sketch on the paper. So some of you were asking me whether do we need to provide all the traces, even though the question is just asking the sketching of the surface. They don't mention about the trace. Yes, you didn't mention about the trace, but you have to. That is part of the step. If you just provide me this in your exam, I mean your answer script, I'm assuming that you are copying from somewhere else. So as for now, you do the exam online, right? So we can say that you just copy from the website or whatever, from the apps. Okay, so we want to see this. Okay, even though you give me the perfect sketching without this, so I cannot give you full mark because you don't provide us the step. Okay, so from every time we want to correct your to mark your exam paper, we have to refer the rubric, the answer scheme. So there is a mark. So in the rubric, there is a mark for this particular step. Okay, again, you have to provide, even though in the instruction they don't mention every single step that you have to provide. So you have to know that. Okay, so and also if you just provide me without this step, so and you don't label, so I'm not sure whether you want to sketch a circle or an ellipse. So everything I will refer to your traces. So from your trace, all the labeling, all the value on the intersection tells me, okay, tell me everything, okay, so I can understand from your trace. Because this one sometimes quite complicated to understand what you are actually sketching about. So I will always refer to your traces. All right. Okay, but look at here. Do you think this is complete? This is a complete surface? I would say, cantik tak? Macam itulah. Is it complete? Yeah, of course not. Because we're not sure what is the shape over here and what is the shape over here. Then we have to investigate further. Okay, so meaning that how can you know that? Then you have to modify the value of z. So you want to know what is the shape when z at the specific height. So maybe the simplest value that we can have is just z equal to 1. Okay, so let's say now we set so z equal to 1. Okay, z equal to 1. So at z equal to 1, okay, at z equal to 1, so what is the function or the equation becomes? So you have to refer to the original expression here, and we set z equal to 1. So when you replace z equal to 1, so we will get x squared over 9 plus y squared over 4 minus 1 equal to 1. So when we simplify, we will get x squared over 9 plus y squared over 4 equal to 2. Okay, so it looks like when z equal to 1, we have, this is certainly not a circle again. We have to make sure this one become 1 so that we can have an ellipse. Okay, so when we simplify, so this one become 18 and this one become 8 equal to 1. Then we have an ellipse. Okay, so which is a larger ellipse, larger than this or smaller than this. Okay, so again you'll have to look at the denominator here. What is the square root of 18 and what is the square root of 8? If you check, the value of them should be greater than, for x should be 18, square root 18 should be greater than 3, and the square root 8 should be greater than 2. Okay, so we have a larger ellipse. So now, what can you do is, we sketch another ellipse on the same y-axis plane. Okay, so I just redraw because we have no enough space here. So you should draw on the same y-axis plane on your previous ellipse. Okay, because level curve, you have to sketch level curve on the similar y-axis plane. Okay, so I redraw again. So the previous one we have 2 and we have 3 on y-axis plane. So we have this ellipse. Okay, and this one we have a larger ellipse. So this one square root 18 and this one square root 8. Okay, so then we label so that we know which is which. So this is for z equal to 0 and this one z equal to 1. So we know that when we set z equal to 1 here, we have a larger ellipse. How about, because you can see the graph here, okay, how can we know that the z can also be negative? So you have to look at from your original expression. Okay, again, I got so many questions about the sphere and hemisphere. Okay, so you have to take note. I remind you that you have to look at the original expression provided. Okay, so in this case, this is the original, not after you modify. This is the original, meaning that in this case, we look at the z. So the z here, look at the z here, you have square. So if we put z 0, or if we put z equal to 1, I mean positive, or z it can be negative. So the function here is still valid, right? So they don't give you something, then the function does not exist, isn't it? Because look at the z here. If you put z equal to 1, so it ends up to be 1 because z 1 squared, so 1. Or I put 2, so it becomes 4, right? But how about if I put negative 2 and negative 1? Still possible, isn't it? So meaning that z can be positive, z can be negative. So in this case, we can set z negative as well. It's not always positive because last time I always show you z positive because of the function itself. Say that z cannot be negative. Remember we have the ball. So what is the equation of ball? Z equal to x squared plus y squared. So now I'm asking you, can z be negative? When you put any value of x, you put x 0, y 0. You put x negative and you put y negative. So the answer is always positive and the smallest value is 0. So that's why I put the z always positive. And you can see from the graph itself, the graph is a ball, but the minimum value at 0, it never touched the line of z negative. The curve never touched the line of z negative. Down here, nothing. So the surface, you cannot find any point when z is negative. So there is no value z negative because from the function here tells you that z always positive. Similarly, for the cone, what is the function, the general function of cone? Square root of x squared plus y squared. So look at the square root here. The original expression is just square root, no negative sign, no positive sign. So we know that in mathematics, okay, if there is no negative sign outside square root, meaning that it is positive. So if you want it to be negative, you have to put negative. You cannot say that the square root can be both positive or not. That is wrong. Okay, so for in mathematics, the correct one, z equal to, if there is no sign, that means positive square root. But if you want to consider both, you have to put both signs, positive and negative. So we understood that z is positive and also z is also negative. Okay. So that is the thing that we have discussed previously. Okay, now we have this particular problem. So we want to finish this. So now we want to investigate what is the shape when z is negative 1. Okay, because why I'm choosing 1? So because value 1 is very simple, right? Okay, so now we replace z equal to negative 1 into the original expression. Original expression. Okay, so x squared over 9 plus y squared over 4 negative. So z is minus 1 square equal to 1. So what is the simplified form? So you will get x squared over 9 plus y squared over 4 negative 1 squared. So 1 equal to 1. So you will get x squared over 9 plus y squared over 4 equal to 2. So that is the simplified form after you replace z equal to negative 1. So now we want to sketch. But before you sketch, now we compare with z equal to 1 that you replaced just now. Hopefully you can see that. Okay, it's quite small. So we have the similar form, right? z1 will have the same as z minus 1. So meaning that they will have the similar graph. You can see that they are the same, right? X squared, y squared equal to 2. And also this one, x squared, y squared with their own denominator equal to 2. So because of the function, both of the function give you the similar expression. So meaning that the graph of z equal to negative 1 will be the same as z equal to 1. So you just put here. So this is the graph of z equal to 1 and also z minus 1. Okay, so now, sorry, wrong ellipse, the larger ellipse. Okay, it should be the larger ellipse. Sorry, I labeled the wrong ellipse. So this one is z equal to 1 and also minus 1. Okay, so what is actually happened here? So we want to say that when z is at the height of z equal to 1 and also z minus 1 down here, so the shape of them are the same. The size of the ellipse is the same. So this one is minus 1. Okay, so when you are standing over here, you can just see this actually 3 ellipse, yeah, but because of we have the similar size, so we can just see 2. So the white one, the white color here, so that is your z equal to 0, and this one, for this one, the striking color you can see here, and you can see also over here. Okay, so now we have this particular surface. So this is called as hyperboloid. Okay, hyperboloid. from, so the name is coming from the word of hyperbolic in 2D, hyperboloid in 3D. Hyperbolic of, so there are two types of hyperbolic. Last time we have sketched the hyperboloid. Now we have another hyperboloid. Okay, so this hyperboloid is called hyperboloid of one sheet. One sheet. Because from one equation you have one surface. So last time, I'm not sure whether we have the sketching on here or not. Let me check. Yeah, this one. So last time, this is also hyperboloid because it's coming from the hyperbolic shape, but it's split into two. So this is called as hyperboloid of two sheet. Because why we call that? Because from one equation it splits into two sheets. So that's why the name is hyperboloid of two sheets. Two, because it becomes separate sheet, right? Separate surface from single equation. And today we have sketched the hyperbolic of one sheet. Okay, so now we know how to sketch the hyperbolic of one sheet. So that's not too hard, right? Just so, isn't it? So you can try sketch again, and you will see that this is not so complicated.